Hi everyone, welcome back. Today we will start a new lesson, chapter 4 of NCERT textbook, Moving Charges and Magnetism. Okay, and we know already a charge at rest produces electric field. When a charge moves, a current is produced. Also, when a charge moves, a magnetic field is also created. If you place a compass needle near a current carrying conductor, you can see that compass needle is deflecting because the current has some magnetic effect. Okay, current consists of moving charges. So when charges in motion, they can create a magnetic field. If direction of current changes, direction of magnetic field also changes. So a charge at rest can produce electric field only. It cannot produce magnetic field. But a charge in motion can produce both electric and magnetic fields. Today, we will discuss force on a charge moving through a magnetic field. Force on a charge moving through a magnetic field. On a charged particle, moving through a magnetic field. Suppose a charge Q moves through a magnetic field of strength B. We represent magnetic field strength by the letter B. Okay. Suppose a charge moves with a velocity V through a uniform magnetic field. So the external field, since moving charges has a magnetic field, it will interact with the external magnetic field. As a result, the charge experiences a force. I will give the equation for the force on the charge. This force on the charge is proportional to the magnitude of the charge. It also proportional to the velocity of the charged particle. It is again depends on the magnetic field and also depends on the direction of motion of charge, sine theta. The sine theta is the angle between magnetic field and the velocity. So here what is B? Strength of the magnetic field. Strength of the magnetic field. V is the strength of the magnetic field. Magnetic fields. V, velocity of the charge. Q, magnitude of the charge. Theta, angle between magnetic field and velocity. You can remove this proportionality sign. We can write V equals a constant K. K is the proportionality constant. QVB sine theta. But the value of K is found to be 1. Therefore, we can write F is equal to QVB sine theta. We can write this force equation in vector form. F bar, Q constant only. You know, A cross B is AB sine theta. Therefore, V cross VB sine theta is V bar cross V bar. This is the force on a charged particle moving through a magnetic field. See, this force is perpendicular to both velocity and magnetic field. You know, cross product of two vectors. Direction of the cross product is given by Maxwell's corkscrew rule or right hand thumb rule. One more rule is there, Fleming's left hand rule. Okay, this force is perpendicular to V bar and B bar. Suppose this is the direction of V. This direction of V. And this angle is measured from V to B, velocity to B. Then direction of the force will be perpendicular to these two. This will be the direction of the force. Okay. We can also determine the direction of force by using Fleming's left hand rule. What is this Fleming's left hand rule? Hold the forefinger, central finger, and thumb of your left hand in mutually perpendicular direction. If forefinger points in the direction of the magnetic field, central finger represents the direction of motion of the charge, then thumb will give the direction of the magnetic force. This is Fleming's left hand rule. Okay, so we can find the direction of magnetic field using Fleming's left hand rule or Maxwell corkscrew rule. Okay. Now, what is the magnitude of the force? The magnitude of the force is F is equal to QVB sine theta. We can discuss some cases, special cases. If theta is 0 or 180, what will be the force? Force will be QVB sine 0 or 180, it is 0. So if a charged particle moves parallel to the magnetic field, it will not experience any force. So remember, when a charged particle moves parallel or anti-parallel to the direction of magnetic field, it will not experience any force. Now, case 2. If theta equals 90 degree, what will be the force? VQV sine 90. So force will be maximum. VQV. So when a charged particle moves perpendicular to the magnetic field, it will experience maximum force. If the charged particle is at rest, velocity is 0, then force will be 0. There won't be any force, magnetic force. Force is 0. Okay, so we can find out the direction of force in another way also. Suppose the charge is moving along x direction. So its velocity will be V into I hat. You know, I hat is a unit vector along X direction. If the magnetic field is along positive Y direction, magnetic field can be written as V into J hat. Then how will you find out, write the force? Q into V cross B. So V I hat cross V J hat. So Q, V, V are magnitudes only, constant. I cross J. And you know, I cross J will be what direction? K. So Q, V, V, K hat. So this force will be along positive Z direction. This force will be along positive Z direction. So this way also we can find out the direction of the force. Okay. You can remember this tool IJK. I cross J will be K. See the rotation. J cross K will be I. K cross I will be J. If it is not coming in order, I cross K will be minus J. K cross J will be minus I. I cross K will be minus J. J cross I will be minus K. In this way, we can find out the direction of the magnetic force. So, when a charged particle moves through a magnetic field, it will experience a force whose magnitude is given by F is equal to QVB sin theta. Here, the force is perpendicular to both V velocity and V. Its direction can be found out by using Fleming's left-hand rule or Maxwell corkscrew rule. Okay, if the charged particle moves parallel to the magnetic field or anti-parallel to the magnetic field, it will not experience a force. Now, if we can define the unit of magnetic field, SI unit of magnetic field from this equation. SI unit of magnetic field is Tesla, capital T. We can define it. See, force equation is BQV sin theta. If theta 90 degrees, Q1 coulomb, V 1 meter per second, then Q is 1 coulomb, V 1 meter per second, theta 90 degree, then we can write and F 1 Newton. Then V will be 1 Tesla. Okay. So V equals 1 Tesla. When V is 1 Tesla, when charged particle, when 1 coulomb charge passes through a magnetic field with a speed V perpendicular to the magnetic field, the strength of the magnetic field will be 1 Tesla. I will give the definition. The strength of the magnetic field is 1 Tesla if 1 coulomb charge moves with a speed of 1 meter per second perpendicular to the direction of magnetic field, experiences a force of 1 Newton. Then strength of the magnetic field is 1 Tesla. Okay. Now, there is a smaller unit called Gauss. written by capital R. It is related to Tesla in this way. 1 goes equals 10 raised to minus 4 Tesla. So what is the definition of 1 Tesla? The strength of the magnetic field is 1 Tesla if a charge of 1 coulomb moves with a speed of 1 meter per second perpendicular to the magnetic field, experiences a force of 1 Newton. The strength of the magnetic field is 1 Tesla. Remember this relation between Gauss and Tesla. 1 Gauss is equal to 10 raised to minus 4 Tesla. Okay. Now, see, we have seen now that when a charged particle moves perpendicular to the magnetic field, force is perpendicular to velocity and v. See, if a force is perpendicular to the velocity, what will be the path traveled by the nature of the path traveled by the charged particle? When a force acts perpendicular to the velocity, the moving particle will move along a circular path. Okay, moving particle will move along a circular path. So when a charged particle moves perpendicular to the magnetic field, it will describe a circular path. Okay. Now, magnetic field moving into the plane of the paper, perpendicular to it, is represented by this into mark. If I write like this, a cross in a circle, that represents a magnetic field moving into the plane of the paper. And if a circle and I am writing inside a dot, that represents magnetic field coming out of the plane of the paper. Okay. So when a charged particle moves through a perpendicular magnetic field, what is the nature of the path traveled by the charged particle? It will be in circular. When any particle moves perpendicular to the force, particle will moving in a circular path. You know centripetal force. When a particle moves around a circle, centripetal force is directed towards the center. That is perpendicular to the direction of motion. Okay. So I am considering this is a magnetic field moving into the plane of the paper. Okay. Suppose the particle at the instant velocity is in this way, direction, force is directed perpendicular to it. So what will happen? It will move in a circular path. In a perpendicular magnetic field, the particle moves into a perpendicular into a circular path. So charged particle is entering here. Okay. When it enters, the force will be perpendicular to it. So what will happen? The particle will move in a circular path. Okay. Force will be towards the center of the circular path. So suppose velocity at this point is in this way, this will be the force. At the lowermost point, velocity this way, force is this way. Okay. So at every point, velocity is perpendicular to the force. So particle moves in a circular path. So remember, when a charged particle move into enter into a perpendicular magnetic field, it will describe a circular path. We can find out the equation for the radius of this path. You know, here centripetal force is provided by the magnetic force. What is the force equation? F is equal to VQ. V here angle is 90. VQV. This provides centripetal force. What is the equation for centripetal force? MV square by R. So this magnetic force provides the centripetal force. That means mv square by r equals vqv. From this, you can find out r. R equals one velocity cancel. You are getting mv by vq. So this is the equation for the radius of the circular path. Radius of the circular path. Here I consider a positive charged particle entered the magnetic field. See, when the positive charge enters the magnetic field, it moves in a circular path. The circular path anti-clockwise direction. If you suppose a negative charge enter, the circular, that direction will be clockwise. Okay, so R equals mv by vq. This is the equation for the radius of the circular path. Okay, children. Now we can find out the time for one complete circular motion. That is known as time period. Time period. T equals, you know, time period, distance by velocity. What is the distance for one circular path? Circumference, 2 pi r by v. You can put the value of r there, 2 pi by v into mv by vq. So we can cut this v. So time period is 2 pi m by vq. See the equation, time period. It is not depending on velocity, speed of the charged particle, and the radius. So time period of a charged particle in a uniform magnetic field is independent of its speed and radius of the circular path. This is an important point. Okay. Now you can find out frequency. Frequency is 1 by t. That will be 1 by 2 pi m by vq. So vq by 2 pi m. F is equal to vq by 2 pi m. So frequency also not depending on speed or radius of the circular path. This frequency is known as cyclotron frequency. Okay, cyclotron frequency. Suppose a proton is entering the magnetic field. So perpendicular to the magnetic field. So you know it will enter a, it will move in a circular path. If an electron enter, it also move in a circular path, but R is mv by vq. Mass of electron is smaller, so radius of the circular path will be smaller than that of proton. Okay, so this is a uniform magnetic field directed into the plane of the paper. Suppose an electron is entering. Electron. Okay, so it will describe a circular path inside. Okay, it will deflect in what way? It will deflect in what way? You can apply Fleming's left-hand rule. Okay, electron is moving towards the right, from left to right. So current, positive charge will be in this way. Magnetic field is into the plane of the paper. So electron will be deflected downward. So electron will move like this. Okay, electron will move like this. Like this. But which rule I used? Fleming's left-hand rule. Electron is moving in this way. So positive charge will move opposite. magnetic field is into the plane of the paper. Force will be downward. Okay. Now, suppose a proton is entering. This is a proton. What will happen to the direction? The force will be in what direction? Positive charge. This way, magnetic field into the plane, force will be upward. So it will move in this direction. And you know, R equals mv by bq. Proton has more mass. So proton radius will be more. So it will move in a circular path of larger radius, right? In this way, we can draw the path of electrons in a electrons or any charge, proton in a magnetic field. Okay. If a neutron is entering this path in this magnetic field, what will happen? Neutron has no charge, right? So it will be going straight only. Because neutron is having no charge. It will experience zero force only. Okay, children? So, by this, today's class ends. Watch the video, like the video, share it. Thank you for watching. Goodbye.